Hello, everyone. Thank you for joining us for today's Deeper Talk seminar. My name is Jared Heiss. I'm the Science Director at CUSSP. Before introducing our seminar speaker, a few housekeeping announcements. Today's event is online. Questions will be answered at the end of the presentation. Raise your hand in Zoom to ask your question live. You can also use the Q&A button at the bottom of the Zoom screen. Along with all previous Deeper Talk seminar presentations, this talk will be recorded and available to view online at institute.surf/deepertalks, as well as on our YouTube and Vimeo channels. If you wish to receive notification for upcoming monthly talks, go to the Connect link at the top of the Institute website. Now it's my privilege to introduce today's speaker. Dr. Kevin Rosso is a senior geochemist at the Pacific Northwest National Lab. He leads the Department of Energy, Basic Energy Sciences Geochemistry program at PNNL, where he's the director of the Subsurface Signals Permeability and Multi-Institution Program funded by DOE's Office of Science. Dr. Rosso is a well-recognized expert in uncovering mechanisms controlling reaction kinetics at mineral fluid interfaces, such as for dissolution, precipitation, metal adsorption, or incorporation and redox processes. His current focus is on addressing key basic science questions needed to advance enhanced geothermal systems. Previous application spaces include metal sulfide oxidation, bacterial reduction of metal oxides, contaminant fate and transport, crystal growth and dissolution, geologic carbon sequestration, electrical energy storage, and stress corrosion cracking. Dr. Rosso won the Meteorological Society of America Award in 2004, the Halleman Lectureship from the Mineralogical Society of Great Britain and Ireland in 2016, and the Strum Medal from the European Association of Geochemistry in 2020. He is a fellow of the Geochemical Society, the European Association of Geochemistry, and the American Association for the Advancement of Science, and the American Geophysical Union. He's been an active mentor for more than 50 postdoctoral researchers, graduate students, and early career scientists at PNNL and abroad. Now it's my pleasure to turn this over to Dr. Rosso to talk about geothermal systems and the CUSSP experiment.
Thanks very much, Jarrett and the SURF team. It's a pleasure to be here with you all. Good morning to folks online. I assume that you can see me and see the screen and hear me just fine. Yeah, today's talk will be an overview, really, of a project called CUSSP, which is the Center for Understanding Subsurface Signals and Permeability. The project is just right now at its 2-year mark. It was launched about this time in 2023, and it's a 4-year project, so we've got 2 more years. We're at the halfway point. And it's focused on fundamental science to help enable enhanced geothermal systems to come online broadly. We'll talk about enhanced geothermal systems. We'll talk about CUSSP, but I can warn you right now that what I'm going to show with regards to the project really is an overview of our motivation, what our long-term goal is, and some let's say vignettes of science that show our progress, but we're not quite there yet. Invite me back in a couple of years when the project is wrapping up, and we'll have a lot more to show. Let me just go ahead and give acknowledgement to the DOE Office of Science for funding this work. It was started as part of the Energy Earthshots initiative. It involves 10 institutions and a very large team. I'll show you some mugshots of our team. But, to be honest, I won't be able to do justice to everything that they're doing to make this project a success. I will try to show you, as I said, some snippets, some scientific accomplishments. So yeah, let's just get into it and talk a little bit about enhanced geothermal systems, so we're all on the same page with what those are. We'll try to, there we go. This is one rendition of enhanced geothermal systems, what it's all about. Most people are familiar with the concept of geothermal energy, but by and large, you think of natural hot springs where you have a surface expression of a natural geothermal reservoir already in place. You know, those are few and far between around the world, and people do use those for generating electricity. But really, to bring geothermal online writ large for energy production that is meaningful for the globe, the concept is basically to establish an artificial reservoir underground. That is to go into hot, dry rock at great depth to create a fracture network in that hot, dry rock so that you can flow fluid through it. And then use that fracture network to connect an injection well where you inject cold water from the surface. The water then flows through the hot rock through the fracture network, extracting heat and then returning to the surface through production wells that take the hot fluid to generate steam and spin a turbine and generate electricity. So this is one rendition from a DOE Geothermal Technologies Office EGS fact sheet 2016. It's one that I use because it's DOE originated, but it's not necessarily the best picture of what's going on physically underground, which is really what the focus of our research is all about. Trying to predict, understand and predict the behavior in the subsurface in one of these stimulated fracture networks is really the scientific white space for CUSSP. So this is enhanced geothermal systems, and based on this concept, there's great potential for electricity generation across the nation to the tune of about 60 million homes in the U.S. Based on these kinds of estimates that basically combine conventional geothermal resources, which are, as I mentioned, few and far between, with these next generation types of geothermal resources where artificial reservoirs are created. And the color map basically gives you just a quick visual as to the regions where EGS has a prospect, and just note that it includes all regions of the country, but obviously west of the Mississippi, there's a lot of potential. It's worth noting that for those of you that don't know, that this is already demonstrated and pretty well established conceptually that this works. This is a pretty famous site supported by the DOE. It's a demo EGS site in Utah near Milford, and it's a project that's been ongoing for a number of years, and its design was basically to not only demonstrate proof of principle that you can drill into hot, dry rock, establish flow and recover heat, but also to use learn by doing as a strategy to improve the technology that is used to do that. It's important to note that all of this is really enabled by advances in directional drilling that the oil and gas industry has developed over the past 20 years, which allows precise drilling and directional drilling at great depth, even in hot, dry rock, impermeable rocks such as granites or granitoids. And Utah Forge is one example where this was done successfully. In this case, it's a doublet pair of two wells, an injection well and a production well, blue and red. You can see that the depths that we're talking about are on the order of tens of thousands of feet. And that is to get into a temperature regime in the subsurface that's on the order of 200 degrees C and up. This is a great site. It's a great project, and I believe this seminar today actually overlaps with their annual R&D aspect of Utah Forge, the program, which is happening. I think its final day of that activity was today. So just suffice it to say, Utah Forge is a great example of success in this area. That demo is not really designed to generate electricity. Startups are showing that they can take it to that stage. Fervo Energy is a famous startup company that has made this proof loud and clear. With Project Red in Nevada near Winnemucca, now generating electrical power for more than a year. And Fervo Energy is expanding, establishing the Cape Station site adjacent to Utah Forge, where they planned to prove that they could generate up to 500 megawatts of electricity using enhanced geothermal systems. So the bottom line here, as EGIST technology, all the way to electricity and power production, has taken off. So it's happening. It's happening around the world as well. So just the basics of the concept in a little bit more detail, so that you can understand the next few slides where we talk about what the challenges really are. So some basics of EGS, right? You need directional drilling. The notion is basically that you need to align your wells along your best guess as to what the direction of the minimum principal stress is. And that is so that when you fracture the rock, you generate planes of fractures normal to that direction. You know, the concept really is to make as densely connected, highly distributed network of fractures as possible. And you want as many active flow channels between the injection and production well as possible. And this cartoon kind of shows you the concept that you might expect, just as a zeroth order approximation, that the direction of the minimum principal stress would lie in the horizontal plane. It doesn't always. Knowing that, you know, from a site characterization standpoint, is sometimes difficult, but nonetheless, I hope you get the concept. So, right, and you're stimulating the subsurface, ideally in a granitoid rock. You don't know what the pre-existing fracture network really is like. You're hopeful that there's a pre-existing fracture network that you can reactivate when you stimulate the fracture network. But you're also probably relying on the ability of that technology to generate new robust fractures. You generate the fracture network, and in principle, you want to avoid fracture closure. That'd be a waste of energy. So the way they typically try to ensure that fractures stay open is they inject proppant, like in many cases, just quartz sand, to physically maintain fracture aperture once you've stimulated the fracture network. So proppant is typically. So one challenge with EGS is actually knowing where you've made fractures. On top of that, knowing which fractures are actually active for flow once you establish that flow through the fracture network. This is just sort of a visual to give you a feel for the fidelity, state-of-the-art fidelity that comes with characterizing your fracture network. And this is basically all the microseismic activity at the Utah Forge site, the accumulated data, spanning the time frame from when they stimulated the fracture network, all the way to when and during circulation tests where they're flowing fluid through the fracture network. It was a 9-day circulation test, I believe, in 2024, followed by a 30-day circulation test. So you have microseismic events, the locations of which give you kind of a visual for what the subsurface fracture network, the active subsurface fracture network, kind of looks like. But this is a feel for the fidelity. You know, the question is, over decades of use and decades of heat production, how sensitive is this particular approach to being able to detect changes in the flow behavior? You know, that is an open question. The reason we expect changes in the flow behavior over long periods of time is because you've got complicated processes associated with flowing hydrothermal pressurized fluid through rocks, many of which the fracture surfaces will have exposed brand new reactive surface area on the rock. So you've got temperature, you've got pressure, you've got stress on those fractures, both from the confining pressure, but also the fluid pressure. And you've got a complex combination of dissolution and precipitation with feedbacks with stress that you can imagine could change the permeability of the fracture network over time and its distribution of flow. In other words, the fluid is going to take the path of least resistance by and large. And as those pathways change in terms of hydraulic conductivity, because of these kinds of processes represented by this visual, you can expect the flow channeling to be different, the robustness of the flow through a dense fracture network to become different. You could also expect things like fast channels to become preferred, limiting flow and cutting off circulation through the largest possible volume of the rock. So heat recovery, this is in question and hasn't yet really been proven. And like I said, places like Fervo, the Project Red in Nevada has been running for about a year with successful heat recovery all along the way. But when you start asking questions about decadal timeframes, there's still a lot of uncertainty. So this is room for fundamental science to basically come in and try and develop the technology and the understanding of these kinds of processes to help eliminate obstacles that are likely to emerge in the future as we do learn by doing and establish these EGS reservoirs. So this is a report in 2015 that I like to go back to because it brought together the thought leaders in this space to think about these problems and sort of do an analysis of where the frontiers should be for fundamental research. And it really talks about understanding basically the state of stress, its distribution in the subsurface, and combined with the geochemical reactivity. And if those kinds of things can be known in as much detail as we can possibly achieve, then there's a prospect for putting this knowledge to work to anticipate problems in reactive transport simulators, reservoir simulators that are designed to address EGS performance. So CUSSP is basically designed to do just that. It was focused on two major objectives. One is to make sure that we have that basic understanding about how fluid pressures, chemical reactions in the hot stressed rock alter flow pathways over time, and to be able to do that from the microscopic scale to the field scale. We also proposed that to address the seeing the network problem, to try and develop new geophysical sensing tools that could add to the current mix of sensing modalities, such as seismic or acoustic sensing or distributed temperature sensing, things of that nature, but to add new geophysical sensing modalities that might help increase the fidelity of understanding of the fracture network. We also ambitiously proposed that we could take those kinds of advances, combine them for a particular field site, and demonstrate that with real-time sensing of flow through a fracture network in real rock at a real field site, that we can show that we can interpret that data in terms of the underlying thermal, hydrologic, mechanical, and chemical parameters that lead to those signals. So we had an ambitious goal, and that is the direction that CUSSP is headed. And we have a roadmap to get there that I'll walk you through really quickly, and then I'll show you some vignettes of success, pieces towards the end goal. Let me first make sure I give credit to the team. This is the team of people that wrote the proposal in 2023 that won the competition. And we're the only funded Earthshot in this particular space, in enhanced geothermal systems. One other focused on wellbore integrity. Ours is really the only one that is designed to address these reactive flow and transport problems for the reservoir itself. The team is star-studded. It's a dream team of geophysicists, geochemists, and geomechanics experts that have rarely talked to each other in the past, but now enjoy regular meetings to put our heads together for these kinds of problems. And there's a website where you can go and get a little bit more detail about CUSSP. I'm going to be trying to represent some of these brilliant folks' thought, leadership, and bits and pieces of success on the program so far. And it goes without saying that none of this work that we're doing could be possible without fantastic recruits at the PhD student and the postdoctoral level, most of whom are shown here, but this team continues to grow. Right, so CUSSP focused its workflow around EGS testbeds that are already available at the SURF site. The fly-through movie that you're seeing there is moving quite fast, but it shows the two EGS testbeds that have been established at the SURF site deep underground. One's at the 4850 level. The other one, this one, I can pause this, I cannot, is the 4100 level testbed. Both of these were established by the US DOE's Geothermal Technologies Office in a program called EGS CoLab, participants of which are on the CUSSP team. These test beds are fantastic, world-class research capabilities for EGS. And I'll tell you a little bit why. I think most people online here will know about the SURF site, where it's located, and why it was established in the first place. Right, so two slides that kind of overview the EGS testbed that we chose to use for CUSSP's R&D effort. Right, so one is the fact that these testbeds are highly instrumented. This picture down below shows the injection manifold that is that allows the flow experiments at the EGS testbed at the 4100 level at SURF. This allows us to do things like stimulation and fluid circulation at selected intervals in a network of wells, 11 wells, 5 of which are dedicated to flow and production. The remaining wells dedicated to sensing. The sensing capabilities at these test beds are phenomenal. At this particular test bed, we've got active seismic, we've got passive seismic, we've got distributed temperature sensing. We've got the prospect and hope to put high-resolution strain meters to get information about deformation during flow experiments. And electrical resistivity tomography, which is a novel modality that I'll talk a little bit more about in a second. Right, one of the things that's very nice about this site, in addition to the fact that you can do these experiments, is that it's got about the right hard rock lithology for EGS. It's a bit more mafic than a granite. In this case, it's an amphibolite that has dense calcite veining within. The reason we like it is because of the prospect that some of its mineralogy may be very reactive, more reactive than you might expect in a granite. But that is good for us because we'd like to be able to do experiments on the timescales of, let's say, months, as opposed to waiting a decade or two. So you see shiny yellowish minerals in this rock. It's an amphibolite that is bearing a lot of sulfides, pyritites, for example, very reactive with respect to oxidation, which releases acid, which then can combine with things like the carbonates to lead to lots of dissolution. So there's a prospect of inducing chemistry changes that we may want to detect the signals for at this particular test bed. Right, ambient temperature, because humans can go down and run these experiments, but gets us in the right stress regime for real EGS. The fractures are that we use at this test bed are hydropropped as opposed to being propped by proppant. We proposed to inject proppant, which is possible to do, but our budget in the end that was allocated did not allow for that. So the fractures are propped open by the fluid injected pressure itself. Other perks of the data of the site is that we've got rich data sets from the EGS CoLab project that we can use for analysis and to develop some of the infrastructure that we need to be able to do CUSSP experiments. I mentioned ERT, and really this is concept is for the EGS problem is led by Tim Johnson on the team. ERT, electrical resistivity tomography, is just based by and large on measuring potential differences between 2 points in space. Once you apply a current generating set of electrodes, if you have a grid of those throughout your well network, in principle, you can get tomography information about the bulk electrical conductivity of your chunk of rock, your volume of rock. One of the things about ERT that's exciting is that it's very sensitive to rock type and confining pressure. In other words, as you squeeze on these rocks, you see a very rapid change in their electrical resistivity, the physics of which at the nanoscale are still sort of poorly defined. It's interesting scientific space for CUSSP to explore. But at the same time, it's very practical, relatively straightforward to implement, and it provides information that is what we think of as orthogonal to other kinds of information in sensing, such as seismic wave velocities and seismic properties of the system. So ERT is something that is involved heavily in CUSSP, trying to understand the signals and to measure ERT responses at the same time that we're flowing fluid through the testbed. CUSSP seeks to basically use designer fluid chemistries and fluid properties to induce changes in the fracture network while we're doing multimodal geophysical sensing of various kinds, including ERT. These are just examples of the kinds of data that were collected under the EGS CoLab project, where you can see in real time when you inject fluid into the testbed. You can see basically where that injected fluid has manifested in the testbed through high conductivity red regions shown in this video. I'll set that back so you can see most of the change happens at the very beginning when injection is occurring. But the cool thing about ERT is that because you can measure the conductivity through the bulk volume of rock, you can actually interpolate what is going on between the wells. So it's not just where you've injected the fluid, but you can now see how that impacts the conductivity of the rock between the wells, which may have something to do with the stress, the state of stress between the boreholes, something that is difficult to access by any other geophysical sensing. So these kinds of experiments are the kinds of experiments we hope to do. We're planning experiments here in this next fiscal year of the project, our first CUSSP experiments that will collect data of this nature. Right, so what are we going to do with that? And this is basically a summary of what our workflow really is all about. We need to, as I mentioned, without getting into too much detail, understand the reaction processes that could be changing the permeability, the conductivity of fractures for the specific lithology of the testbed. We need to be able to input those process rates into models designed to mimic the field experiments themselves. To do that, we have to define simple, efficient analytical expressions that allow us to take that process understanding and to put it into continuum scale simulators so that we can use those simulations to provide synthetic data that can be combined with the observed data and analyzed with techniques such as machine learning, surrogate models, to fully understand system behavior and to show that we can predict system behavior through this iterative process of developing better and better models, proven accurate through direct testing at the test. Right, so let's just get into some of the things that we're doing in sort of vignettes, as I call them. pFlowTran is our chosen simulator. We've got a fantastic team of experts coding up the capabilities needed to be able to simulate our EGS testbed experiments specifically. Right now, we've got folks working on enhancing pFlowTran in terms of its mechanical treatment of the geomechanical properties of the system, and how that's coupled with other processes, such as on the chemical and hydraulic and thermal fronts. So yes, it's a continuum approach. We're modeling the entire system with multi-continuum treatment. It's not to say that we don't use other approaches in the modeling, just to make sure that we're understanding how fractures are behaving, such as discrete fracture network modeling, which is also something that we're doing. But for the test bed, we've had specific enhancements in our ability to mesh the system. We've had folks working on developing automated meshing capabilities that can be used to generate hypothetical fracture network renditions for input into P-Flow-Trans so that reactive transport simulations can be run. This is just an example of Chuan Yao's work that has allowed this to be automated and allow the team basically to generate multiple visualizations of the fracture network at the test bed to perform forward reactive transport simulations that predict behavior and signals. These are some just examples of the kinds of signals that we can now predict for various scenarios of fracture network possibilities at the test bed. In combination with liquid pressure information, predictions of liquid pressure distribution throughout the test bed. We've got predictions of strain on the fracture network. You can imagine that properties of the solution that impact conductivity would be an important aspect to simulate for ERT monitoring. And so tracer concentration is something that we're hoping to involve in our experiments. The ability to model the tracer concentration as a function of time is built into our simulator, along with the change in the electrical potential distribution at any point in space and time. So I mentioned the core scale studies. We're using the actual rock sampled from the test bed for detailed stress strain fracturing geomechanical characterization and reactive flow and transport simulations and microscale studies. These are just some of the examples of this amphibolite rock that has been analyzed with synchrotron-based microtomography and has continued to be analyzed using that technique to understand how it fractures and how the fracturing relates to things like the foliation or the fabric of the rock, and also the extent to which fractures may propagate along veins through the rock, such as the carbonate veins that we know are there. This is just an example of monitoring the fracturing of some of this amphibolite in situ using X-ray microtomography. Yes, here's an example of the kind of spatial information that you can get from this as a function of the stress applied and the strain. You can see basically in brown where the fractures are, what their geometric characteristics are, what their roughness is over time, and that information can then be used for things like reactive transport simulations, because now you have a geometric feel for what the fracture network kind of looks like. And because of the correspondence to the mineralogy of the rock, you might also be able to develop, chemically informed reactive transport simulations of these fracture networks, because you may know one fracture, for example, resides in a calcite vein versus another fracture, they may actually just follow along the amphibolite fabric. Right, so this kind of information can be sort of automatically converted into simulations using sort of a digital rock physics approach that allows you to predict things like conductivity, hydraulic conductivity of the fracture, or also its reactive properties. I think that's all we've got on this one. Our geochemistry team is working on trying to predict what the reaction network might be for a given fracture set of physical properties, but also the mineralogic distribution and flow direction through that fracture. You can imagine a cascade of reactions from highly reactive minerals that then lead to changes in fluid composition that have impacts on the mineralogy downflow. So precipitation of things like clays is something that we expect over the long term, but more rapid reactions that we know are going to be important are things like calcite and metal carbonate dissolution, as well as oxidation of these metal sulfides. So we've got designer fluid chemistries that we're hoping to use in CUSSP to basically induce those reactions, show what signals can be in terms of ERT or perhaps even changes in flow behavior during our flow and circulation experiments. And it's not just all theory and simulation, because there's a lot of microscale studies going on in the laboratory using abstractions of the problem to try and understand mechanisms of reactions and reaction rates for the actual fluid compositions that we expect at the test bed, given the mineralogy. And these are just some examples of micromodel studies to look at things like calcite dissolution as a function of fracture properties and solution conditions, using fluorescent optodes that are chemically sensitive to things like calcite or calcium concentrations in solution. We're doing microscale studies using microscopies of various kinds to look and make sure that we understand what the complex fluid electrolyte composition, how it impacts dissolution rates of nominally idealized minerals. The geochemical literature is replete with rate information on idealized minerals, but not for complex systems where you have impurities, defects, and multi-component solutions. So we need to understand basically how other cations in the system may or may not impact the behavior of mineral dissolution or reprecipitation, and especially the rates. And this is just an example for the very fine scale work that we're doing to understand dissolution behavior in the presence of competitive cations. Right. Those detailed studies have to be translated into efficient analytic expressions that can be used in the continuum simulations of P-flow trend for the site. We've got fantastic minds on the problem of taking high resolution numerical simulations of mechanistic processes such as coupled flow and dissolution and reprecipitation into these continuum expressions. And that is a very valuable, I'd say, scientific front for CUSSP that has been making great strides. So we're putting a lot of energy into trying to understand how detailed microscopic information can be readily represented upscale in these testbed simulations. And that is a difficult problem that I think CUSSP is way up front. I'm going to go ahead and wrap us up because I know we're running out of time and I can't represent everything that we're doing in CUSSP. And at the same time, we're not done. As I mentioned, we're only 2 years in. We've got a lot of moving parts. Everything's moving forward towards this common goal. And it's making great progress. And again, 2 years from now, I'd love to come back and give you a talk about how all these pieces that I've just kind of quickly represented, how they fit together for CUSSP's main goal. It's worth noting that we really enjoyed last Halloween having our first in-person all-hands meeting as a team. We got to meet each other, many of us, for the first time face-to-face at SURF. We converged on the site. The SURF folks were very generous with their time to get us underground to go see the 4100 test bed directly for hands-on visual, and to just get that immersive experience with again, this proving ground for CUSSP, where we're going to do these experiments and prove that we can predict the outcome, right? Just some other pictures of the team. This fantastic core archive there for that particular test bed. We have team members that regularly go to the SURF site to access some of that core and bring it back, distribute it to the team for studies, so that we build that fundamental understanding for the site itself, so that we can produce the most predictive and accurate models for our test bed experiments. Yeah, it was a cold and chilly day. We had a refreshing douse of snow for the photo, but it's a wonderful site, and it's a fantastic research facility. And CUSSP has felt very welcome and very at home there. Yeah, there's news. The synergy between our project and Sanford, the surf site and its mission is totally clear. And so there's articles about that. And I think at this point I've run a little bit long. So why don't I just open it up to questions and discussion? Thanks for your attention.
Wonderful, wonderful, Dr. Rosso. We enjoyed hosting you and your collaborators last year, and look forward to seeing the science come out of the site on the 4,100-foot level that you and your team are heavily engaged in. So let's go ahead and open it up for questions. I see one online from Luke Frash. Do you want to repeat the question if you're able to see it, or I can read it out?
I can't see the question, I'm sorry.
Okay, let me go ahead. So Luke asks, or first starts by saying, thanks for the talk. What proppant will hold up at 250 degrees Celsius for longer than 5 years? And what will the permeability or conductivity of the proppant be?
Okay, great question. I don't know that anyone says that proppant will hold up, as you say, for that long or without evolving. Quartz sand, I think, is typically used because it's a robust form of silica. It's cheap, readily available, and it kind of works, at least for the near term. It doesn't mean that the fractures won't eventually close, or the proppant won't slowly become embedded into the fracture walls, right? So, or the proppant itself could slowly dissolve. There's the conditions at depth, as you know, are fairly aggressive. So, yeah, there are companies out there working on designer proppants, ceramics, even conductive proppants. I don't know if any of that will ever be embraced, to be honest. I think that's up to the practitioners, but as far as I know, there's no widespread adoption of, let's say, designer proppants. But it's a really good question. It's an important aspect of EGS for the proppants to function and work properly. And emplacement of the proppant itself is kind of a black art. It's no guarantee of success. It just is known to help. So I think research on that front is a great direction. And I think Utah Forge, the GTO program there, the research and development program, is supporting some efforts for proppant performance.
Good.
I hope that answers the question.
All right, another question here. What can you say is the real takeaway so far? I see lots of tools, lots of measurements, lots of details, lots of people, great people. But it isn't clear how to connect the work to something that can inform field operations.
Yeah, inform field operations. We hope to just do one thing in CUSSP, if I can, and that is predict, show that we can predict the flow behavior in this test bed, in this one experimental platform. We don't propose to be able to then all of a sudden solve everyone's EGS problems. We propose that we can basically sense and properly interpret changes in the flow behavior in this one experimental test bed. And these are obviously not full-scale EGS dimensions. This is a small scale, intermediate scale experimental platform. We just want to show that we can establish that predictability using a very focused location, with a focused goal in mind. And obviously there's a lot of work to, I think, to get there. And I would say that success along those lines would be way out in front of what is currently available for any kind of practical EGS applications. There are simulators out there. They're being used, but I don't think they've addressed the real concern for EGS deployment writ large, and that is the uncertainty in the long-term performance. I don't think you'd see any EGS practitioner out there right now saying, okay, I've got a simulator. It seems to be working right now. I'm going to rely on this for the next 20 years for my EGS site. I think that would be a far cry. So if we can do that for an intermediate scale EGS testbed and show that for a given set of injection conditions and injectate chemistry, we can properly interpret interpret the outcome and predict what that outcome is actually going to be. I think that is an advance that would be world class. I think it would be really commensurate with the goal of the project itself and what the DOE is trying to do with fundamental science when it's headed this direction. So yeah, I'm talking in generalities, but I just want to make sure we're clear that we're not saying that the output of CUSSP is going to be adoption and instant solution for all EGS field sites. We're not saying that. Our goal is a bit more focused. Hope that makes sense. Other questions?
There's one more follow-up on that one. The follow-up question is, what does that achieve? Model validation? Practically speaking, it's not possible to have all the required data required for prediction at this type of commercial site.
Correct.
Yeah.
Correct. So it'll be a data limited. All simulations will be for real EGS sites will be data limited, right? So yeah, I think one has to take what we're trying to do as an abstraction of the problem, but showing that we can make accurate predictions for a given test bed through test bed experiments, sense predict, and close the loop on that cycle. I still think has value because it shows that it can be done, and it shows what it takes for it to be done. Practitioners ultimately may not head that direction, and it may not necessarily meet the demands of the entire industry, right? But it is a flag in the sand, and that's what fundamental science is all about: establishing what is possible. And I think in the long run, you find that establishing what is possible does come around as a checkpoint for decision making in the future. So we're trying to establish what is possible and push that flag in the sand way forward. And I think it will be hard to beat. The flip side of that, of course, is that it may be hard to implement, but it is a reference point. And I think these reference points are important. Again, talking philosophically, but the whole thing has a long road to hoe. The whole enterprise of EGS has a ways to go. We're just trying to stay out front.
Okay. I think we have another question in the Q&A queue from Rudra Mitra. Let me scroll down here. Oh, yeah, he just thanked you for an interesting talk. Other questions?
Oh, you're welcome.
I had a quick question. You mentioned Forge a couple times. Wonder if you would elaborate or expand your comments on potential connections between Forge and SURF. Are there any questions so far or expected from Forge that would be answerable at SURF?
That's a great question. I like that question because we've been carefully watching what is going on at Forge. as a geochemist, one of the recent results from Forge that I found pretty interesting is that there is evidence for downhole precipitation, mineral precipitation in the fracture network. And you expect a lot of mobilization of silica, and they see that. And you expect the carbonates to be reactive. The thing about many of the metal carbonates, most of them in fact, is that they're retrograde soluble. So you inject cold water that may be saturated or close to saturated with respect to calcite or other metal carbonates. All of a sudden, you hit several hundred degrees Celsius in that fluid. You're going to lower the solubility of the metal carbonates. They will precipitate out. And the paper from Stuart Simmons out of Forge, as recent as just a few months ago, shows that they see evidence in the production outflows for loss of calcium, loss of magnesium over time, which they attribute to precipitation at depth in the reservoir. So, and that's just after a few days of fluid circulation. So the question is, what happens after 10, 20 years? Now, that has the prospect of really changing the flow pathways, creating short circuits that might limit heat recovery. They're not doing long-term experiments at Forge, but the proof of principle is there. Chemical reactions appear to be very, very rapid. Mineral mobilization is, I think, everyone in EGS space would anticipate that mineral mobilization of various kinds is definitely happening. I know that sites like companies like Fervo, I think at their plants, they're using scale inhibitors, so-called scale inhibitors, to limit metal carbonate precipitation. And I think this introduces a lot of questions about whether you recirculate a fluid as it approaches its new equilibrium composition with respect to the formation conditions, or whether you try to cycle out some of the solutes. So yeah, Forge is showing that geochemistry is important in the near term. So it kind of reinforces the picture that it could be important for the overall heat recovery in EGS applications for the long term. So we're looking at that, by the way. So the carbonate chemistry at the test bed at SURF is one of the ones that we're really focused on, because we know it's probably going to be one of the most reactive mineral phases for precipitation and dissolution. And that lithology has quite a bit of carbonate in its mineral composition. Does that help?
Oh, sure, absolutely. What is the time frame for tests at Forge?
Tests at Forge.
You mentioned some of these long-term tests may not be appropriate for Forge. I wasn't sure how long Forge was intended to operate as.
I actually don't know the details of that. My understanding is that they're sort of entering a new phase, and someone else affiliated with the Forge program would have to be able to pick up on that. I don't know if anyone online would know the answer, but I think it was a 30-day circulation test that Dr. Simmons reported on this recent paper where they see this evidence for precipitation at depth.
Another comment here, appreciating your overview. Maybe one more quick question. I'm almost embarrassed to ask it, but I'll ask it anyway.
Sure.
Comments on artificial intelligence, machine learning, AI, ML. I assume some of those tools are being developed for geophysical research. Any comments on that?
Yeah, well, it's an important part of what we're doing. We're trying to improve the simulator, our peak flow trend simulations, its capabilities. And then right now we're in the process of generating several thousand forward simulation scenarios, the output of which will be used to train a machine learning model to generate basically a synthetic data set that can be used for comparison with measurements for these upcoming field experiments. So Yes, the machine learning is super important to what we're doing. We are talking about lots of signals coming simultaneously from these proposed experiments, from both the seismic sensing and the ERT, hopefully strain sensing. And so it's how to properly model these complementary but disconnected data sets. I think it's something that we rely on machine learning and surrogate models to help get us down the road. So yeah, machine learning is very important. Not so much AI, as far as I know.
I think we're coming to the end. Any last quick questions from the attendees? All right. Well, thank you again, Dr. Rosso, for sharing your expertise and for answering all of the questions that our audience had. So as I mentioned at the top of the program, this talk is available to view and share on YouTube, Vimeo, and our Institute website, institute.surf/deepertalks. Next month's Deeper Talks will be on October 8th at 9 a.m., our usual time slot. It will be held in person at the Sanford Lab Homestake Visitor Center. There'll also be a virtual component. The topic will be Homestake to Surf, the Early Days and Beyond Dune, with featured speaker Dr. Jose Alonso, who is our first laboratory director. Your feedback helps improve the program, and we appreciate any questions or suggestions, for speakers and topics for future talks. Please fill out the short survey that you'll receive immediately following the talk on Zoom and in your email. Once again, thank you for attending today's Deeper Talks seminar, and we look forward to seeing you next month.